In this chapter, we discuss image denoising algorithms that are based on the SparseLand model. Let's recall what we have done so far. We introduced the SparseLand model and then rushed to use it for image deblurring. This was done in the crudest possible way with a fixed dictionary and a naive global modeling. Well, now that we have knowledge of dictionary learning methods, it is time to do things in a more systematic and more productive way. In this chapter, we go back to the very beginning and discuss the simplest inverse problem, image denoising. We will introduce a series of practical algorithms for removing noise from images, all relying on the SparseLand model. We start our story on denoising by defining this problem clearly and discussing its importance. I took my cell phone, here it is, and got this photo of my office. And yes, I turned off the lights before doing so in order to strengthen the effects that we are about to discuss. A lovely image, don't you think? Wait, are you sure? Let's zoom in on these regions and see the details. This is one portion of the image, magnified. Here is a second portion, and this is the third. Have you noticed how poor is the spatial resolution and how horrible are the artifacts and the spatial noise? Is this unique to my cell phone camera? Not at all. Almost all images we work with suffer from some sort of noise effect. Those are caused by the sensor and the surrounding electronics. And if this is not enough, the compression and the demosaicing of the digital data contribute to this mess by introducing their own artifacts. So removal of noise from images is a true need. By the way, this issue becomes more severe when the illumination is poor, and many of our photos are exactly like that. Let's define the denoising problem formally. The image X is assumed to be an ideal image. It is contaminated by white additive Gaussian noise of zero mean and variance sigma squared, giving us the image Z. So Z equals X plus V. Our goal is to take Z and try to recover from it an image that will be as close as possible to X. Everything we shall do in this chapter has to do with the design of this box of denoising algorithm. Those of you who have seen some work on denoising may have heard of a different kind of noise, Poisson distributed. Here, on the other hand, we chose to define our problem with the additive Gaussian noise. So let's say a few words on the Poisson case. The two noise distributions we discuss are shown here as conditional probabilities of the pixel Z given its origin X. Poisson is not an additive noise model, and it becomes relevant in low light imaging, in which we should refer to Z as an integer count of photons. Why have we preferred the Gaussian over the Poisson? Because of several key reasons. First, Gaussian noise is much more common. Secondly, when there is a Poisson noise but it is not severe, the behavior gets very close to the Gaussian case. When the Poisson noise becomes stronger, there is a beautiful trick called the Anscombe transform to turn it into an additive Gaussian one. So even in this case, we can get back to the Gaussian regime. Finally, we have to add that many of the ideas that we are about to present could be used for the Poisson case with little adjustments. So now that we have resolved the decision about the noise being Gaussian, we come back to the main track of the discussion. Why are we studying this problem? The first and the prime reason is the fact that in many situations images are noisy and we need to fix them. A second reason to invest in denoising is the fact that it is a terrific platform for exploring ideas in image processing, since it is the simplest possible inverse problem. Let's briefly explain what we mean by that. In its most general form, an inverse problem aims to reverse a degradation effect. If an ideal image X goes through a degradation of some sort, followed by an additive noise, the inverse problem would aim to use Z in order to get back X. In image processing, we typically assume that the degradation is a linear operator, denoted here as H. Such inverse problems are common in imaging and include deblurring, demosaicing, inpainting, tomographic reconstruction, super resolution, and more. As we have already said, denoising is the simplest possible inverse problem in which H is assumed to be the identity operator. We already gave two great reasons to deal with the denoising problem. Here is a third. If you have a good denoising algorithm, you could do various other things with it. Let's explain that in more details. Suppose that we have a terrific algorithm F, capable of removing additive Gaussian noise from an image Z while preserving its true content. Using this function, you could do several other things, such as create artistic effects, suggest various new decompositions of the image into different scales, dehaze, or otherwise treat the dynamic range of the image, and more. Beyond all these, you could even use this function F to solve any inverse problem. Yes, this is a very strong statement, and it is true. You could suggest an algorithm that applies a series of denoising steps and simple things in between, and get a solution to the general inverse problem. Since our focus in this course is on SparseLand, we will not expand further on all of the above. So, denoising is an important problem, and this has been acknowledged over the years by our research community. There are thousands of papers dealing with this task and proposing algorithms. Here is a graph that shows the number of papers published in each year on this subject, and it is clear that the topic is very hot. When we look at the denoising algorithms as proposed over the years, we see an evolution of ideas that gradually led to better and better results. The evolution is very much in line with the evolution in models we discussed earlier in the course, which took us from the L2 and the Wiener filter, passing through robust statistics and PDE, all the way to the more recent sparsity-based methods and more lately neural networks. Let's now dive into this story and show how SparseLand could be used for the benefit of noise removal.